So this is a linked network. It's a little bit more complex than what we've seen before. And here we have E that is essentially linking the first and the second part of the system. So the question then becomes, what happens if E does not work, or what happens if E does work? So we will use a decomposition approach to this. We will consider two scenarios. One where E does not, this one, E does not fail, meaning E works, and then another one where E does fail. So if E does not fail, then essentially we have two systems that are in parallel and in sequence. So let's call this system 1, or part 1 and part 2, not system, but part 1 and part 2. And here is the failure of A, here's the failure of B. The product of them subtracted from 1 gives us reliability for 1. And then the same thing, here we have failure for C, failure for D, multiplied, subtracted from 1, and that's reliability for the second part. So the product of these two is reliability for scenario B, as we have considered here, and this is where E does not fail. So all of these linkages are there and strong. Okay. Then the next one is where E does fail. So if E fails and we don't have all those connections going through, then essentially we're looking at two series that are working in parallel. Let's call this 1. Let's call this 2. So reliability for this system, this scenario C, is essentially 1 minus the failure of 1 times the failure of 2. So how do we define failure? It's 1 minus reliability. So again, looking at reliability of I, or for the top series, we have reliability of A times reliability of C that defines the reliability of that series right there. So we can write RA times RC. The same thing, the failure of 2 is 1 minus reliability of 2. But how do we define that? Again, that's a series in sequence. So reliability of B times reliability of D. So in that fashion, we can get this equation that you see here. So now we need to put it all together and compute the reliability for the system. So we add the results of first scenario and the second scenario. But in the first scenario, remember, we have E working, and in the second scenario, E is failing. So we multiply the reliability or probability of success of E by the reliability of scenario B. We multiply the failure probability of E times the reliability for scenario C, and then we add them together. So reminding us of what those results were from scenario B and C, and assuming that we have these numerical values for reliability of A, B, C, D, and E, then we can plug those numbers in here, in these two, and get these answers right here. And once we have reliability for B and C in a numerical manner, then we can plug them in reliability equation that we found, relationship that we found, and we get the overall reliability of the system to be 0.9858. We could solve this problem with an enumeration method, given that we have A, B, C, D, and E, or 5 components. 2 to the 5 is 32 different combinations that we can run. Now, only several of them are shown here, but you can see that we have the system outcome shown in one of the columns. So in the first run, or in the first enumeration, we have all the components success, and so the system is successful, and we have this probability. But in the second one, we have A failing, and all the other ones are working, and still the system is a success. The system can operate, and eventually we get to a situation like this, where we have A and B both failing, and if A and B both are failing, then the system will fail, and we don't even need to compute the probability for that. And there are and this list will go on for 32, and ultimately at the end, if we add up the probability of success for the system, we will get the 0.9858, which is what we found in this previous slide.